We'll have a panel discussion. And in the last part of the panel discussion is open for questions. So you could also ask questions from the focus talks. So Frank, there's your clock.
Oh, very good. Hello, I hope you can hear me. Yep, perfect. I'm aware I'm between you and coffee, so I'll try to be brief. On the program, you'll find issues in gravitational wave detection and inference. I thought this was a bit too negative, so I changed to challenges. And I'm not going to talk about the methods of detecting inference, but using, since this is a modeling panel, using gravitational waveform models in those applications when they're confronted with real data. And I think to put the summary up front, because I know this is exhausting to listen to, there are two big challenges, I think, that we have now, and that will only become worse as future instruments coming along. One is of computational nature, the computational costs of these analyses, and the other one has to do with accuracy. And previous speakers have touched upon them, and so I'll take the opportunity to say a few more words about some aspects. So today, obviously, I'm not running these things myself, but people in my group and in the LIGO collaboration and beyond that, and analyzing gravitational wave events, let's say of LIGO, typically take between a few hours, if we're lucky, up to a few days. And then, there's new collaboration, it takes another few days. And so easily weeks add up to analyze a single event. That will become worse as we get more events, as the events become louder, they start to overlap and so on. I think that's fairly obvious. Also, we're still analyzing a fairly limited parameter space. We assume the sources are eccentric. We don't account for environmental effects. Probably this is all fine. Most likely this is all fine. But it might not be a good assumption for the future. If you think of in the future, we want to run a binary black hole analysis, maybe not even just black holes, of an eccentric precessing object that includes effects beyond black holes in some non-trivial environment, including calibration effects and glitches and so on. This will become a very high-dimensional parameter space to analyze. And last but not least, now all the signals are very short, and the movement of the detector we can neglect. This will not be true in the future, certainly not for LISA, but also for the Einstein telescope for long signals. On the other side, accuracy, we've seen in Harold's talk, for instance, that models have made great progress and they are remarkably accurate, but they do have actually a significant number of, I don't want to call it errors, but uncertainties. It starts with numerical relativity resolution error and ends with all of the extra effects that aren't even included. And we know that the requirements, and Ricardo had said this, and I'll say a few more words as well, they scale with the SNR. Well, the power depends on what exactly you mean with accuracy, but they scale with SNR or SNR squared. So we're all waiting for louder signals, and as the instruments become more sensitive, signals will become louder. But so our accuracy requirements will increase. And yeah, this is not a typo. So the same thing that we're looking forward to also puts greater demands. And I think systematics will become, or may become, actually I'm going to say they will become the dominant source of uncertainty in our analysis in the future. And we should seriously think about how to deal with this. And I will show some examples or some proposals of how to do this at the last part of the talk. Okay, I've got one slide about computational challenges. I'm not working myself on this too much, so I relied a bit on literature. Obviously, some simple estimates, as I said, as the detectors become more sensitive, they have a greater volume to which they look. If the sources are uniformly distributed, the cube of the horizon distance is the number of signals related to the rate of the signals that we see. So we'll see more signals. But also the length of, let's say, an in-spiral signal to leading order scales like this is a bit messy. This is the chirp mass. This is the starting frequency. So if we compare, let's say, a binary Newton star signal, either we analyze it from 30 hertz or from 3 hertz. This is, obviously is one order of magnitude in frequency, but in time, this is a factor of greater than 400, I think 460 or something, if I did the calculation right. And this is a major challenge. The segments become much longer that we analyze. Again, the detector response becomes time dependent. But also all these data compression techniques we are so used to now, they will become challenging. And in fact, these authors here, this year, in the abstract, they conclude that standard data compression techniques become impractical and the full problem becomes computationally infeasible. So they are actually putting their foot down and saying, what we do right now will not be good enough for things like ET. And the example that is here on the right, which is from this paper, is a binary neutron star signal like 170817 in, I think they assume, cosmic explorer type instrument. You know, the SNR will be above 1,000. And then they look at a specific compression technique called reduced order quadratus that we use today to analyze binary neutron stars. And they show up to what SNR could they do this. Okay, so they, you know, assuming you want a certain accuracy, you can calculate up to which SNR can I actually do this compression. And it turns out that analyses from, I think, 16 hertz onwards, they are still fine with current computing capabilities. But if you want to analyze it starting at lower frequencies, you can only do this, you know, accurately enough for an SNR that drops very sharply. And actually, below SNR, whatever this is, 8 or so, no, it's 12. This is completely infeasible. And they say, you know, even if you take Moore's law into account and you think, okay, every 2 years our computing capabilities will double, that might not be good enough. And maybe we need completely new techniques. Even in the paper, they mention machine learning. And some people will be disappointed, some will be relieved. This is the only time I'll mention machine learning in this talk. Okay, now switch to accuracy requirements. Ricardo showed this already, so I'll go through this very briefly. Of course, today we are used to, when we analyze a gravitational wave event, we express the source properties in terms of a probability distribution, and there's some uncertainty, and this is typically associated with the noise, with the random, that we assume Gaussian noise, statistical uncertainty. But if this signal model that we use to get this posterior isn't quite right, isn't accurate, we might get a wonderfully looking posterior here in red, but it's just wrong, it's inaccurate, it's offset. And the difference between them, let's say the difference between the true signal and what I infer with my wrong signal is called statistical bias. And I'm not going to go through this now in great detail, but I still put it here, I think, for those who have seen this before. One can make simple estimates saying, well, if I neglect the random Gaussian noise part of the signal and say, okay, the signal really is, sorry, the data is really the signal, analyzes with some model that depends on some parameters. Well, you know, this is the first order approximation. This is something like 2 times the SNR, the signal to noise ratio squared, times the mismatch. And we've seen the mismatch before. You can also say, well, let's assume this is more or less Gaussian. It's equivalent to a linearization. So here the Fisher matrix shows up. So then I have a Gaussian distribution. For a Gaussian distribution, I can answer the question, how far do I have to go off in parameter space to have, let's say, 90% probability? And this is this number, this comes up here, is the chi-square distribution with k degrees of freedom. So it depends on whether you look at a 1-dimensional or 5-dimensional, whatever distribution, and the probability that you want to encompass. And then you put these two things together and say, well, if my mismatch is smaller than a certain number, this is of order unity, or maybe of order 10 or so, it has to be less than this, and it scales inversely with the square of the SNR. And this is very frequently used in the literature, but it's a very, very conservative estimate because it doesn't take into account the direction of the difference. If I have 2 waveform models, they're different. I can now calculate, I can only use them up to SNR 10. I use them in an analysis of an SNR 50 event, and it turns out they give identical results. How is this possible? Well, it is possible because the difference in 2 waveforms, if I project them onto the waveform manifold, they could be entirely perpendicular. They could not affect parameter estimation at all. Would be a problem for detection, would be a problem for testing GR, but not for parameter estimation. Or all of the error could go into a parameter that I really don't care about. Maybe by just adjusting the phase, suddenly my waveform models agree very much. Okay? And there's a nice paper by Thompson et al. This year who illustrate that. So this criterion really has to be used with care. And what they show here is, this is a biased analysis of an artificial event. This is the true parameters. This is what they get. And now it depends very much on what question you ask whether you say it's biased or not. For instance, if I ask the question in the two-dimensional M1, M2 space, at what point does my 90% credible interval not include the true parameters anymore? The answer is SNR 60. Up to SNR 60, it would be more or less okay. If I ask what is mass 1 or what is mass 2 individually, the SNR until it gets biased is 250, right? So it really depends on what question you're asking. And I think this kind of thinking we need to get used to for certain tests, for certain analyses. Quick models that are okay-ish are fine and give unbiased results. For other deep analyses, like testing GR or certain tests, I might have to invest a lot of computational power with the most accurate models I have. And so this plot we've seen before, regardless of where you are on these sort of lines, this is a study from Pura and Hassler in 2020. They put a lot of effort into estimating exactly what is this prefactor in front of the 1 over rho square scaling. But regardless of where I am here, as the SNR goes up for future instruments, my requirements will go as negative second power in terms of the mismatch. And if we look at models today, you see mismatches quoted of the order of 10 to minus 3, actually now some 10 to minus 4. You've seen numbers in Harold's presentation. Numerical relativity is a bit better. These are these bands, this is supposed to show our current state of inaccuracy. And if you want to stay within these bands, well, okay, the SNR will go up. So all you can do is get your mismatches down. But again, with this caveat, it really depends on what question you're asking, what analysis you want to do. And we've seen these plots, actually almost exactly these plots in Harold's talk, so I'll be very brief. As examples, these are two events with somewhat similar SNR. Both of them were above 20, I think. And this one is in a parameter space that is well covered, and you see the difference between the phenomenon EOB model at that time is very, very small, whereas this one is in a parameter space that is not so accurately modeled. And so the differences between the models, if you look at the total mass or the mass ratio, are huge. So this systematic over statistical error today is anywhere between the order of maybe a few percent, negligible, to order of 1, where it's not negligible anymore, depending on what you're interested in. Signals like that, if the SNR would be 100 times stronger, probably our models would be fine, would give unbiased results. Signals like that are already a challenge. What? No, this scales with SNR. This does not scale with SNR squared, but this scales with, the mismatch scales with SNR squared. Anyway, we can talk about this over coffee. Right, so, okay, so this is great. And of course, the message is we need to pay waveform models to get the waveform models better. We need to run more accurate NR simulations. But I also think that we really need to think differently. When I'm being asked, what are the properties of 150914? I'm a physicist, I'm proud of not saying, oh, it was 30 plus 32 solar masses. That's not the answer. The answer was, I'm 90% certain that it's between whatever, 29.5 and 31.7, okay? That's how we're used to thinking of astrophysical events. However, with models, we're not like this. If you ask me, what is an equal mass non-spinning model? Okay, there's one waveform. And I think this is not quite right. I think actually, rather than giving best guesses, I think future waveform models should give like a bundle of waveforms. This is the type of signal that is consistent with our state of knowledge. And here's an example. Okay, you have to have eagle eyes to see something from Sebastian Kahn last year. We did this for a simple non-spinning, I think, equal mass signal. So of course, if the accuracy is very high, our confidence is very high, this bundle will look like a single waveform. But you see that here, for instance, in the ring down, there's more uncertainty. And what happens, hopefully, oh my God, okay. What happens, hopefully, is that as we include these systematic errors, this does not magically correct itself without a penalty. But, the inference then becomes broader. We account for our lack of knowledge or uncertainty in the waveform model. It becomes broader, and hopefully moves in the right direction, and thereby gives a more conservative estimate, but one that we can trust in, rather than this one that looks like we can trust in it, but it's wrong. All right, and there are various methods. I will speed up a little bit because I want to talk about some recent work that I was involved in. There are various people have thought about how to do this, either looking at different models and mixing up their posteriors, or using these tuning coefficients that Harold Pfeiffer has introduced in his talk as well, and give them as sort of uncertain probability distributions. Or we provide error envelopes. Sumit Kumar, who is smiling at us from the lower right corner here, and Max Melching and I, we have worked on the model where we, very similar to calibration uncertainties, we say, well, a waveform really is its amplitude plus some small error, and a phase plus some small error. The important difference between calibration uncertainty and our approach is this is a relative error. And then we let the data decide how big is this error. Does the data actually prefer the waveform model to be slightly different? And here's a lovely example, 1911-09, where if you look at the different models, it's not terribly wrong, but it doesn't look nice. On the right-hand side, it even depended on what kind of data we were looking at. Was it the deglitched frame or the original frame? The inference was slightly different, okay? So now we repeated this inference, allowing the waveform model to tweak itself a little bit, add some uncertainty. And what turns out is that we get much more robust results. And then here, it didn't even matter whether we analyzed the deglitched frame or the frame that included the supposed glitch. It all gave much more robust, consistent results. And we can even look at, this is now the phase deviation where the issues appeared. And this was here between 40 and whatever, 70 hertz. And this is important because astrophysically interesting statements like the spin is negative or there's some negative spin in the system, it could have disappeared with adding extra uncertainty, but it didn't. We're very happy about this. And I'm sorry I overran by a few minutes, but I'll leave you with a summary and take a few questions. Thank you very much.
Thank you. Thank you, Frank, for a very nice summary of these. We have a time for one quick question, actually. The closest person.
Okay, so since when you are allowing for this delta A and delta phi, so it is fitting better. Does it mean that there is some say effect that we have not accounted for, which has been missed in the previous waveform, and you are picking those things as this delta A and delta phi?
Yeah, you can interpret this. This is a very good question. You can interpret this in various ways. The way we started off was that our model isn't perfect. It's the best approximation of general relativity, but it's not perfect. So the actual general relativity waveform will have a slightly different phase and slightly different amplitude. So we allow the waveform to correct itself. But you can also think about, we haven't included all of the physics, so we can pick this up. We haven't modeled the data properly. So, and this is what we think is happening with this example I showed. It can actually account for sort of a miscalibration of the data, for instance, in certain frequency bands. So it can pick up all sorts of stuff, which sounds great. The downside is, because it's so versatile, it could also absorb interesting effects that we want to look for. We want to look for a deviation of, I mean, with this addition, like tests of post-Newtonian coefficients will be very difficult because they are absorbed in our uncertainty. But I think we should debate, what is our confidence level?
There was another question.
Hi. So I didn't quite understand, when you say you generate many waveforms in certain range. So it will certainly increase the waveform generation, right? When you say with some delta values.
Also a good question. Yes, I didn't mean necessarily that you have to generate all of the waveform at once. The way in practice it often works is that, in parameter estimation, you try out various different systems that you want to test. Okay, it's now asking for a binary black hole system, 10 or 20 solar masses. And it only generates one waveform. But which waveform it gets it comes out of a distribution that makes sense. So there's uncertainty parameters that you marginalize over. So in your sampling, you would still only produce one waveform every time you jump. But for one set of parameters, multiple waveforms could appear out of a distribution.
Okay, so if there are no further questions, let's thank Frank again. And we break for tea now. We come back at noon.